Remember, we stated exploratory data analysis begins by looking at one variable at a time. This is called univariate or descriptive analysis. In order to convert raw data into useful information, we need to summarize and examine the distribution of any variables of interest. The variables of interest are the variables of interest to you, the researcher, in answering your research questions, addressing your research problem, and telling the story you wish to tell with your research. By distribution of a variable, we mean what values the variable takes and how often the variable takes those values. Here's an example.
A random sample of 1,200 U.S. college students were asked the following questions as part of a larger survey. What's your perception of your own body? Do you feel that you're overweight? About right? Or underweight? This table shows part of the data, 5 of the 1,200 observations. Information that would be interesting to get from this data includes what percentage of the sample students fall into each category. Or, how are students divided across the 3 body type image categories? Are they equally divided? If not, do the percentages follow some kind of pattern? There's no way that we can answer these questions by looking at the raw data, which are in the form of a long list of 1,200 responses. That's just not very useful. However, all these questions will be easily answered once we summarize and look at the frequency distribution of the variable body image. That is, once we summarize how often each of the categories occurs. In order to summarize the distribution of a categorical variable, we first create a table of the different values or categories the variable takes. How many times each variable occurs, which is the count, and more importantly, how often each variable occurs, which is expressed by converting the counts to percentages. Now that we've summarized the distribution of the body image variable, let's go back and interpret the results in the context of the questions that we posed. What percentage of the sample students fall into each category? How are students divided across the 3 body image categories, and are they equally divided? You can see that most of the samples, that is 71.3%, felt that their weight was about right, and that a comparatively small percentage felt underweight at 9.2%. The overweight category was 19.6%.
For my research question, I'm interested in looking at the association between how much a person smokes, that is, quantity and frequency of smoking, and the presence or absence of nicotine dependence. Going back to the NESARC codebook, you may recall that I have a number of variables that measure smoking behavior and nicotine dependence. It's the actual name of the variable, rather than the longer descriptive name, that I'll include in my program in order to generate frequency distributions. I have the names of each of the variables circled here in red. Now go back to your Python program to generate frequency distributions using the value counts function. The value counts function is part of the Pandas library, and you will need to load that library each time you run Python in order to use the function, as we did in the first line in our program. Here I use the value counts function to generate frequency counts for my nicotine dependence variable with the following code. C1 is a new name that I have chosen to represent the nicotine dependence counts. Since each variable only exists as part of the data set, we again need to tell Python where to find that variable by typing the name of the data set, or in Pandas lingo, the name of the data frame, followed by the name of the variable, tab12mdx, within both brackets and either double or single quotation marks. Next, a period followed by the value underscore counts function. Like all functions, value counts allows for input inside the parentheses. Here we include sort equals false, so that our data will be displayed in the order of the variable's original values rather than sorted by the actual counts. To ask for percentages of each value based on those counts, the code is similar, but after choosing a name to represent the nicotine dependence percentages, P1 here, we also include the syntax normalize equals true within the function's parentheses. To get either counts or percentages for each variable, separate lines of code need to be written. In addition, we need to explicitly ask Python to print these distributions so that we can run multiple lines of code simultaneously and will generate the output we are interested in examining. Remember, choose a name to represent each count or percentage distribution. My example is C1, C2, P1, P2, etc. here. Include the names of the data set followed by the variable name within brackets and single or double quotation marks. A period followed by the function name value counts, and then either sort equals false for counts or sort equals false, comma, normalize equals true for percentages. If we run this code, the distributions of interest will be displayed in the console, but we will not be able to easily determine one of them from the other. To handle this, it's helpful to include titles or labels. One simple approach is to use the keyword print followed by text that describes the requested analyses. So here's our code thus far. We've set the working directory, imported the Pandas and NumPy libraries, loaded our data set, and now written code that provides the frequency distributions, that is, counts and percentages, for each of the values for our variables of interest. Again, before you run the program, save it by clicking the Save button under the File menu, and then select Run under the Run menu. You can also run specific lines of code or groups of code by selecting the lines and choosing Run Selection or Current Line from the Run menu. Once your program has finished running, the commands, the output, and any error messages will appear in the console window. So the next step is to scroll through the console to see the output or results that were generated. In this example, I know my program has run successfully because there are no error messages in the console window and my output is displayed. If you type the name of a variable incorrectly, this will commonly be indicated by key error, followed by the incorrect variable name you have typed. If you do find any errors listed, go back to your program or script, correct the errors, save the corrected code, and then run it again. Let's look at the frequency distributions that were generated. Given that the variable names are rather cryptic, we might want to print statements to be a bit more interpretable. Since the print function in our code is just asking for the text strings, we can actually change them to read however we would like. Here I've added additional information in each of the print lines. Let's look here at the output, which shows the distribution of responses for the variable tobacco dependence in the past 12 months. The NESARC codebook shows that 1 means yes and 0 means no. Following this list of response options, the output also shows the frequency of each. In the next list, we see the response options followed by corresponding percentages of individuals with and without nicotine dependence, rather than the frequency counts. By consulting the codebook, you can interpret and describe each of these frequency tables in the same way. Here we see, for example, that 38,131, or 88.4% of the sample, do not meet criteria for nicotine dependence in the past 12 months, while 4,962, or approximately 11.5% of the sample, do meet criteria for nicotine dependence in the past 12 months. When we scroll down to usual quantity when smoked cigarettes, S3AQ3C1, we find that the values are displayed in an incorrect order. A value of 1 for that variable is followed by a value of 10. A value of 19 is followed by a value of 2, etc. This is happening because Python is reading the values as strings or objects rather than as numeric, because it encountered empty cells when reading the column for that variable. To correct this, we can add a line of code to our program, converting the variable to numeric before calling on the value counts function. To do this, identify the variable of interest, specifying the data frame that the variable is drawn from, and convert the variables to numeric by using the input convert_numeric equal to true and closed within parentheses. It can actually be a good idea to do this for each of the variables you'll be working with. So if I save and run the program, and look at this new output, I can see that the distributions are now all numerically ordered with the same counts and percentages we saw in our earlier output. You will note, though, that the missing or blank category has been dropped from the output, and counts and percentages are still based on the entire sample, including these missing observations. To display missing data, add the drop NA equals false option to the value count statement. It's important to note that this new code, converting variables to numeric, should be placed after the syntax that calls in or loads the data set, and before the syntax that requests the frequency tables. That is, after Python has access to the variables in the data set and before the output on those variables is requested. I want to point out that with most programming languages, there are often multiple ways to accomplish the same task. Bigroups is actually another approach to frequency distributions, both counts and percentages. As with the value counts approach, I select a name that will represent the nicotine dependence counts, here CT1. As always, since each variable I'm interested in only exists as part of the data set, I need to tell Python where to find that variable. That is, in data, the name of the data set or data frame. I also include the name of my variable, tab12mdx, within both parentheses and either single or double quotation marks. Next, a period followed by the word size, followed by empty parentheses. Finally, I ask Python to print CT1. To ask for percentages with the bigroups approach, based on those counts, the code is similar, but after the empty parentheses, I add a time sign, that is an asterisk, the number 100, / len, which stands for length, and then data, the name I have given to my data set within parentheses. Again, the step of converting all of the variables to numeric is also a good habit to get into when using the by function, so that your frequency distributions are ordered according to their numeric values.